So we have a sort of a progression here. In number 6, we have a positive point charge at rest, creating just an electric field. And then number 7, we have that same positive point charge, and now it's moving to the right with a constant speed. It already, of course, has an electric field, but now that it's in motion, it has a magnetic field as well. So in our last situation here, we're going to take a look at what happens if it's not moving at a constant speed. What if it's accelerating? Now, you probably don't have any more room on the paper here to draw this, so we want to transfer over to your handwritten notes. So we want to draw a pretty large diagram of what's going to happen here. Alright, so let's imagine an oscillating, vibrating point charge. So it's going to be accelerating, going back and forth. So here's a picture of it. Here's the point charge. Let's say it's sort of shaking, oscillating, vibrating back and forth through large oscillations, maybe like simple harmonic motion, like a mass on a spring sort of thing. We're going to set up an observer to watch this happen, just to record the effects of any sort of changes in the field. So over here we'll draw an observer. Let's say it's a top-down view. There's a person's head, and their shoulders, and their arms, and their torso, and their hands sticking out of their sleeves, and there's their legs, and there's their feet, right? So head, shoulders, knees, and toes, right? And you can just draw a smiley face for all I care, just draw a circle, it doesn't matter. But here's our observer. Now clearly this is not to scale, otherwise this is the largest point charge you ever saw, or the tiniest little observer you ever saw, but that's not the point. The point is that this person, this object, this person's going to be watching the object oscillate back and forth and recording what happens to the field. So let's consider the electric field first. It is a point charge, so of course we're thinking of the equation, E equals kq over r squared, and the charge moving through these large oscillations. So let's say here it is in the middle at the distance of closest approach, but it's going farther and farther away, right? So if the charge is going farther and farther away, what will our observer measure happening to the electric field? Well, the field's going to get weaker, right? R gets larger, field gets weaker. So as the charge goes over here, it's getting weaker and weaker and weaker, and then stops and turns around and comes back, and here it's coming back towards the middle. It's getting closer and closer. So what will our observer register happening to the field? It's getting stronger. As R gets smaller, E gets larger, right? So it gets weak over here, then it gets stronger, then it goes through an oscillation all the way over to here, and so it's getting weaker, stronger, weaker, stronger, weaker, stronger, weaker, stronger, weaker, and so it's going back and forth, back and forth. So let's plot what a graph would look like. So let's say here's the axis of the graph, which is going to be sort of on an angle like this, and you'll see why, and make sure you're drawing it the same way I am. And it's going to starts at 0 and it goes to strong, and then it goes to 0 and it gets weak, and it goes the other way, strong, weak, strong, weak, strong, weak, and so it's going to have sort of an oscillating pattern, almost like a sinusoidally varying shape to the electric field. Now this point charge is in motion, which means it's acting like a tiny current. It will also create a magnetic field as it's moving back and forth. Let's consider what's going to happen there. So here it is going through like simple harmonic motion, and we know it's moving the fastest in the middle, and then of course it's got to slow down, slow down, slow down, eventually coming to rest instantaneously over here. So when it comes to rest, when the speed is 0, how much magnetic field does it create? Well, none whatsoever. It's a very weak magnetic field. It's getting weaker and weaker until eventually it goes to 0 because, of course, it's not moving. But then, of course, it's going to speed up as it comes back towards the middle. And here it's going the fastest in the middle. So the magnetic field it's creating is the strongest. It's like the largest current. And it goes over here and slows down and stops. The magnetic field is weak, strong, weak, strong, weak, strong, weak, strong. In fact, the magnetic field is going to oscillate in a very similar pattern to the electric field, getting stronger, weaker, and those positions of strength or weakness occur at the same positions where the electric field was strong or weak. So we're going to have a very similar pattern. But if we go back to our concepts, or to our electric and magnetic field page here, let's take a look at problem 7, where we see a specific relationship between electric field direction and magnetic field direction. Above this point charge, the electric field points to the top of the page, and magnetic field points out of the page. Down in this region, the electric field points to the bottom of the page, and the magnetic field points into the page. In any region there, what's the relationship between the direction of the electric field and the direction of the magnetic field? They're at right angles, right? Up and out, down and in. No matter what, the electric field and magnetic field are at right angles to each other. So the magnetic field is going to oscillate in the same way, in sort of a sinusoidally varying pattern, but in a sort of a horizontal orientation. So it looks like this: left and right and left and right, like that. And this is a picture of the magnetic field created by the oscillating or vibrating point charge. If you're having trouble visualizing this, I'm going to put some arrows. So here are some arrows pointing up and down for the electric field. Here are some arrows pointing sort of left and right for the magnetic field. Hopefully you should be able to see the electric field sort of pattern, I should say. The electric field graph oscillates in the vertical dimension. The magnetic field graph oscillates in the horizontal dimension. Can you see that? They're always at right angles to each other. Now, what's actually rather interesting about this is that the effect of this positive charge vibrating back and forth, this effect of the changing electromagnetic field, actually isn't localized around the charge. It actually propagates through space. So the axis here, we can actually put an arrow on the end of it saying that this effect actually travels through space. I know this is all rather confusing, but we've actually seen this. We've seen this before. Maybe it didn't look like this, but we've seen this effect before. I mean, it should be very striking, this sort of sinusoidally varying shape. What does it remind you of? Hopefully it reminds you of a wave, right? This looks like a wave like in the vertical direction, looks like a wave in the horizontal direction. And so we're looking at a wave that's a mixture of an oscillating or vibrating electric and magnetic field that travels through space. We've seen this before. What is this? This is light, right? An electromagnetic wave. We've said that light is created by accelerating electric charges. Oh my gosh, it all comes together. It all comes together. So everything we've been doing this year comes full circle. This is amazing. This discovery was made at the end of the 1800s, where huge connections are being drawn. That now they see that light is really a combination of electromagnetic fields. This brought together a whole lot of physics. In fact, at the end of the 1800s, physicists around the world sort of thought that they were kind of done with physics. They realized with Newton's laws and conservation of energy and conservation of momentum, they could solve pretty much any problem in mechanics. And then in electricity and magnetism, a guy by the name of James Clerk Maxwell came along, and he realized that all of electricity and magnetism boiled down to just 4 equations. And with those 4 equations, they could solve pretty much any problem in electricity and magnetism. And then with this discovery, that light is really the connecting thing between electricity and magnetism and waves and optics and all that, they sort of had everything. And they thought at the end of the 1800s that physics was done. And so they were rejoicing. They're like, oh, we're done with physics. All we do is solve problems. And so they set to work just trying to solve as many problems as they could. It turns out they were completely wrong, but that's a story that will be continued in the next video.